Good morning and welcome to all the webinar participants. Today we have prepared a very interesting topic, EMAG bin picking automation reaching in the box. But first of all, the questions may you ask yourself, when do I use bin picking automation? What do I have to consider and where are the limits of this? This and other questions will be answered on this webinar from EMAG. Before we start, I would like to show you how you can give us your questions. First of all, you have the possibility to type in your questions in the chat so we can see your questions. All the participants can see this, or anonymous on the question box also. Before we start, I would like to introduce myself. My name is Meinhold Johann Klein. I'm almost 20 years in the sales business, including 7 years with the EMAG Group. As a regional sales manager, I have the privilege of advising our customers in south of Bavaria. Okay, Kevin, let's start.
Yeah, thank you, Meinhold. Let me introduce myself too. My name is Kevin Schumacher. I work for EMAG since 2.5 years now in the robotic department. I do robot simulations, programming, and everything that comes in touch with vision-guided robotics. And therefore, I am the right guy to guide you through this webinar today. So with that said, let's straight up begin. First of all, I'd like to give a little overview of about today's topics. We obviously will start with the introduction and the basics. We will talk about what bin picking is. We will talk about the reasons why you should use bin picking in your productions. And also we will talk to the difficulties that may occur and what you have to consider when doing bin picking operations. At the end of the introduction, we will have a look at a little animation that we prepared to give you a better overview, and right then we can start into the more technical details. We will talk about the differentiation of different use cases of robot-guided systems in general and about different camera systems. From there on, we want to talk about workpiece and box geometries. This is where it will be getting interesting for everyone working in logistics and in process planning, because we want to talk about the materials themselves and on how they interact with each other. And also there we will have a look at different testings and images we took to show you how the systems work and what difficulties you may find when using. And also obviously how to counter those difficulties and what to do when. After that, we will talk about the emptying rate and part gripping, discussing how much parts can get out of the box and how they will be getting out of the box. And also about customizable robotics, where we will talk a lot about flexibility and about the important topic of collision-free path planning. At the end of our webinar, we will show you a cell concept that we built and brought into production, where we can see raw parts gripped by the robot, brought into the automation process and palletized the finished parts. So let's dive into the first topic, the introduction, what is bin picking. And if you go ahead and simply ask Google what bin picking is, you will find different definitions. I have here a definition from the Fraunhofer IFF, and it is described that bin picking in classical case is a robot-assisted removal of unsorted parts from a container done by a camera system to recognize the position and the orientation and then to take out the parts flexible, reliable, and fully autonomous. So what is bin picking for our understanding? First of all, it is obviously a camera-guided robotic system that is very flexible for feeding in raw parts into the machining process, and thereby it offers a very high level of autonomy. As a little side note, I'd like to mention that it differentiates from depalletizing of pre-oriented parts. What is similar because you pick up parts and bring them into the machine, but it has a lot of differences. But that will be discussed in a few slides. So let's go ahead and talk about the reasons for bin picking. In my opinion, there are 5 very big reasons why you should use bin picking as an autonomy system. So first of all, flexibility, because you don't have a lot of setup times on robots or camera systems, because you can handle a large variety of parts without changing anything but the program, and that can be done completely automatic. And if you have to change something, it's nothing more than the gripper. Also, the installation area, because space is always a topic, and for a bin picking system, you need very little space. For example, the new MRC that has been developed by EMAG recently, and that you can see on the AMB in Stuttgart this September, it only takes around 2.7 meters times 5.1 meters, and therefore it's not big. It's in fact in the same size of any normal machine. Next topic is loudness. We all do know the noise that is made by other mechanical separators, and that gets annoying over time if you work for long term in the production. And with bin picking, this is no topic at all, because a robot can take out a part almost completely silent. And as an economic advantage, you do not have to have a worker standing all day by the machine for feeding in parts into the machining process. And bin picking is one of the few separation systems that do not need someone standing there all the time. Also, it is integratable. You can combine the bin picking robot with additional automation solutions. May it be a belt conveyor, a track motion, a portal, or buffle solutions of any kind. And additionally to that, you can also integrate the robot into different handling operations, like loading periphery stations for graving, for measuring, and so on. But also, on the other hand, we do have challenges when doing bin picking operations. And one of the big challenges is the complexity that you will find. Because we do have a very large variety of parts that we can handle, but for every part we do need a different camera program for recognition of those parts and for picking them. And also for the robots and the PLC, there need to be done adjustments. But all of this is done in front loading and not during your production cycle. Also, sometimes the parts are very difficult to grip out of the containers, or sometimes even difficult to recognize on their exact position, but that will be discussed later in detail. For now, we can say that you do definitely need some expert knowledge to implement a bin picking system and to optimize it so it will work collision-free and you will have a significant increase of productivity. Second challenge you will find out is to select the right manufacturer for your bin picking system, because on the market there is a large variety of manufacturers too. To name some of them, for example, Keyence, Cognex, MagMind, I'm very sure that the big part of you already have heard those names in combination with vision systems. And for EMAG, we decided to use 2 different manufacturers for the systems that we use. That is, on one time, it's Keyence that we use for 3D bin picking operations, and Mikado from Optonic that we use for depalletization. But to discuss what's the difference between those two, we will come in a few slides. Now I'd like to talk about the process chain. What happens during bin picking and how does the process look like in a few details. We won't go too deep into the technical, but let's have an overlook. First of all, we need to do some 3D image capturing, and to generate a 3D image, we use a strip light projection that shows light strips on the raw parts vertically and horizontally, and on the intersection of those points, those lines, we get points that can be recognized by the cameras, and here we get a height information. And to get a height information out of an image, we need at least 2 cameras that are angled to each other. And after doing this, we generate a so-called point cloud of thousands of those points. With that done, we can go into the evaluation and the matching process, where we will overlay the 3D geometry that we have of our workpieces with this generated point cloud, and there the algorithm will check where does it match, and therefore we get information where parts are placed and in which orientation they are. After that is done, the algorithm will select one part that suits the best and is easiest to access for the robot, and then we go to the path planning that will be done collision-free. And to do so, we will calculate multiple support positions for the robot movement and the final gripping position. By that, we compare the 3D geometry of the robot and the gripper system with the 3D images that we just found out by the camera, and also lay out data from the CAD or different areas that we log out of the process. With that done, we are at the reaching into the box point where the robot starts its movement to pick up the part. And here we have to say, as a little notice, camera-guided robot movement does not mean that the camera always looks what the robot is doing, but it more means that the camera checked where the robot can go and then tells him to do so. And with those 4 steps, we picked up our first part. So now we have a little animation for you where we can see a VL3 Duo machine flanged to a bin picking automation cell. Here we can see we have an inlay gripper, we have obviously the shuttles for the machine for loading raw parts, taking up the finished parts, the robot itself, part storage if needed so, the bin picking camera as a heart of the whole system, and 2 boxes for feeding in raw parts and bringing out the finished material. Now we can see here the robot loads the first position and then takes the finished part from the first operation and loads it to the OP20, because we can obviously work on both sides of the machine. Here we can see again, placing the first raw part, changing the second part and picking up the finished parts into the bin. Now that the first layer is finished, the robot will automatically change the gripper system, pick up a blister for the next layer can be started. Everything of this goes fully automatic. So let's go on to the next topic today, camera and robotics. Differentiation of the use cases. Like I said, we have different use cases, but first let's talk about camera-guided robotics in general and the differentiation between camera concepts. We have steady cameras on the one hand and robot camera systems on the other hand. For static cameras, we can place them very high in the automation cell where we do have enough room to give the cameras themselves large distances between each other. We can integrate a powerful projector for the strip light projection, and due to the high mounting position, we do not have any risk of damaging the camera during the automation process. On the other hand, if we build smaller, we can use a robot-guided camera system that is mounted right to the flange of the robot and will be carried by the robot. Here we have a small distance between the 2 cameras, and either we don't have a projector at all or this one has to be mounted separately. And since we do move the camera around, there always is a risk of damaging. So for EMAG, we decided to use static camera systems. So, bin picking and depalletization. I talked about the 2 different systems earlier. Let's have a look at the situations and the requirements that both systems bring with them. On the one hand, bin picking systems do work with chaotic raw part locations, and we can access various containers where the parts are brought into the system. On the other hand, for a depalletization system, I mostly work only with one type of container, and I have the parts already pre-oriented, so I only need to get the location and not the angles where the parts are oriented. So this brings different requirements with each other. For bin picking systems, we do have the recognition of the part position and to find out in which orientation the part is. And also we need to find the best fitting gripping position, considering any interfering geometry, maybe from different machines, maybe from the container itself or other parts that are also in the container. And there we do need to do a lot complex calculation of the path. On the other hand, when doing depalletizing systems, we don't have to spend that much effort because we only need to recognize the part position. We already do know the orientation. We know there's nothing around the part. We can send the end position to the robot and he will start movement straight up.
Kevin, let me jump in with the first question from the audience. Thank you for the question. Am I faster with bin picking than with track motion, automation, or SCS?
Those two systems are kind of hard to compare to each other because for a SCS system with a track motion, I have defined positions where I can pick up the part and where I place the part. With a bin picking system, I am much more flexible, but the picking of the part is much more complicated. And sometimes when I do a bin picking operation, I can take the part out in an ideal spot. I have it secure in the gripper. I can feed it into the machine conveyor directly. Then I am at around the same cycle time. But if I do have to do some regripping at an orientation station or something like that, then bin picking will get slower. But bin picking definitely is always more flexible.
Okay, thank you.
So back to the camera-guided robotics. We decided today to talk about bin picking systems. So depalletizing systems shown, but not any topic anymore for today. Let's go into the technical details where it will get much more interesting for production planners and logistic. We will talk now about the workpiece properties. We will discuss what raw parts are suitable for bin picking and where we will find out limits. Optimal are parts that do have a matte surface, cast iron, forged materials, anything like that. And the more simple the geometry is, for example, a saw cut, the better I can take the parts out. When I do have parts with shiny surfaces, may it be pre-machined steel, aluminum, anything like that, and I do have shiny reflectations, then I can't get any height information on the position where I have the reflection. So it gets much more difficult to take out the parts because I can't recognize them that good. When the geometry also starts to be repeating itself or is interlocking in each other, just think about some tubes that have been bent. It's also getting more complex because when I try to lift one part, I may lift another too. And what's an absolute no-go for any camera system is transparency. For example, acrylic glass, anything with foils, because I can't get any height information at all.
So
I'd like you to remember those parts shown here on the orange line, shiny material and an interlocking geometry. We may see them later again. But first let's have a look at the containers. What is suitable here? Every large standard container is in general suitable for bin picking. Steel crates, Euro pallets with wooden frames, mesh boxes, absolutely no problem here. As the containers are getting smaller, like those shown bulk boxes here, it's getting more complex to pick out the parts collision-free because the space the robot can move also gets smaller. But still possible, no problem here. If we have some rough frames shown as the fourth option here, it gets difficult because the parts may lock into the frame and I can't simply pull them out. But if I do have large parts that can't lock into the frame, this is also no problem. All I have to make sure is that I can see the edge of the frame on top. if the containers are overfilled and there are too many parts and they are building little mountains, it's getting difficult to recognize them because the camera system may interpret the geometry of the raw parts as an interference geometry and won't go there. And also parts that are too big for the containers that are lapping out are not pickable because the camera won't either recognize them or also recognize those parts as an interference geometry.
Let me interrupt you
Yes.
once again. We have another question from the audience. Can the exchange of the collection basket also be automated in combination with bin picking?
Absolutely. It's no problem for the camera system if I change the boxes by hand, when I take them out manually, or if I do use an HEV, for example, that will take out the empty boxes and feed into new parts. HEV can tell the robot cell what part type is worked on next, and then we can simply go into production with an HEV completely automatic. And this also improves the automation, the autonomy of the whole production line if you use HEVs.
Okay, thank you.
Okay, to the next topic, I'd like to change to the testings that we have done previously. Here we can see a test image in monochrome, so in grayscalings from outside of the camera position. We can see the blue frame, which is the searching area to check if the container is in the right spot. And the green area tells us this is the inside of the container where the part matching will take place. So if you take a look at those parts that we have here, we have simple saw cuts, easy to very, very easy parts to do in bin picking. What we can see here is that we have an evaluation value. This is between 95 and 98%. This represents how good the matching algorithm is on those parts. For example, on the standing upright part, the algorithm is to 98.7% sure that there is a part. And this is an extremely good match. Everything about 60% evaluation is considered good and pickable. Also, you can see that there are letters for the search model A and B in this case, where I have the B letter for standing upright part and the A letter for the flat laying part. This tells me what kind of grip the robot will perform to extract the part out of the container. And this also is used for placing the parts into the machine conveyor, into buffer systems or anything like that, because this definitely interacts with the robot positioning. So to get a better look at the height information that we get out, we can change to depth grading, where we have colors shown. Red closer to the camera, blue, the guiding lines on the bottom are the most distant point to the camera. Nothing changed in the box itself. It's the same image, the same 3 raw parts. We only have a color grading now to get a little bit of a better feeling how the camera sees those parts. So for now, let's say we hide the bottom of the box because we do not care on what is below those this threshold, because there's nothing we can pick. And it's better for us to elevate what we can see. Now you can see that there are 3 yellow lines, 2 on the right side and 1 bottom left. And now it's the question, what is shown here? We do have additional parts in those baskets that had there been all the time. But now it's the question, how do we get those parts? We can switch here to different grippings and also to different search models. For example, we can search for only the half part or a quarter of the part to separate those parts out of the edges into the middle of the box and take them out then. Therefore, we do use undefined grips. What an undefined and a defined grip is, we will talk about later. First, let me show you the picture of the basket itself, how it was placed below the camera. And now you can see that there are 2 additional parts in here. It's not 6 parts, it's 8. And we did not see those 2 at all. So First of all, we have to say parts below the flanged edge of the part of the container are badly visible. And in this case, we also placed the box out of the center of the camera. So on the one side, we had accessibility. On the other side, we did not. And during the next slides, I want to take you to talk about the emptying rate of the container. How many parts can I take out and what is necessary to get them out? And for now, we have to say the emptying rate contains about the components themselves, geometry, material, how the surface is, and on the container and its geometry, and therefore how they two interact with each other. So let's go to the next topic, emptying rate and part gripping. Now we want to talk about how do I get the parts out that are not placed optimal, because everything placed optimal in the middle of the box or on top of it is easy to access. But if it gets difficult, there we take a closer look. Now we have a scheme of the container cut in half. We can see the flanked edges, and on top of it, we do have the projector with the two cameras. The evaluable area is always within the projection, and we have to make sure that the container itself is fully visible for the cameras and the projector. And everything inside the projection is the area where we can find parts. Everything outside won't be considered. So now we have the angles of the camera, what they can see, and below the flanked edges, we do have a shadowed area where we cannot access, because if you take a look, the left camera can look on below the flanked edge of the left side. So how do I prevent this shadowing? First of all, I have to make sure that the camera is in the optimal distance. I can see the whole box, and my focus points are placed in the middle of the camera, in the middle of the container. And always I need to check that the positioning of the container itself is in the middle below the camera to get an optimal picture of it. This can be achieved by guiding lines or anything like that. Then I can do a lot by selecting the right container. I can select some with as small as possible flanked edges, and if I cannot take them out, I have to deal with them, but if possible, I can select a container without flanked edges at all. But now if I still have parts that are tiny and that roll below the flanked edges and are in the shadowed area, I can think about inserts and rolling aids for those parts. Those can be placed by hand, or if I do have containers that are only used, think about welding them in. With those box inserts, I can absolutely make sure that every part will roll a little bit to the middle and cannot be in shadowed area, and therefore I have an emptying rate on 100%, and I will get every part out of the container.
Kevin, let me add an information. All these topics can be done as a tryout, right?
Correctly.
The EMAG to be sure that all these topics are working, right?
Yes, if we get in touch with a customer and we talk about a project, it's always a possibility that you as a customer send parts to us, and we can check if they are if they're easy to evaluate for bin picking and if they will work.
Thank you. We had a question from the audience. How much service is required for the camera system?
For the camera system itself, there is no service required at all, because it's an optical system. We won't get in touch with anything, so there won't be any damage and therefore no maintenance. For the robot system, there will be like the electric maintenance, but this will happen every time you use the robot. But you won't have any extra setup that is needed for the camera and anything maintenancing.
That's great. Thank you.
So let's get back to talking about the emptying rate. The next topic on emptying rate after shadowing is interfering geometry. And by interfering geometry, I can get areas where we can't access parts. This interfering geometry can come from inside the container by foreign bodies, like the cuttings of too long parts of the transport foil, or to damage by the container. On the right-hand side, we can see two pictures of containers packed in transportation foils. And if you look at the top right picture, we can here see that there are also interference geometries from outside possible. Like in this case, there's a cover plate that hasn't been removed completely. And this plate will be recognized by the camera system. And therefore, we will have areas where the robot may not move. Also, if you do use a transport foil for preventing of corrosion, you should make sure that the foil gets stretched. Because if you look at the bottom right picture, we can show this in color grading for height information. And as you can see, you can't even tell what kind of container has been used. Is this a steel crate? Is it a Euro pallet with some wooden frames? We just can't know because there is too much interference geometry from the foil. So if it's necessary to use a foil, you always need to make sure that it will be stretched to the sides. I talked a lot about different part gripping separations, about removal from the container, and about separation of the parts. So let's have a closer look to that. We divide into two different grip types. First of them is to remove parts from the container. This is the most of the time the bin picking system works. Herefore, we have two requirements. First of all, the geometry must be fully visible, and the robot must be able to reach a defined gripping position. On the other hand, we have to separate parts inside the container. Therefore, the requirements are only that the geometry is visible in parts, and we don't need a defined gripping position. We can use an undefined gripping position. Now, what is a defined and what is an undefined gripping position, you may ask? Let's have a closer look. First of all, the defined grip. If the raw part can be gripped securely and in correct position, and I do not have any chance that the position of the raw part in clamped situation will change, I can take out the part of the container and feed it right into the machine shuttle or buffer system. If I can't access a defined grip position, I may be able to access an undefined gripping position, where the component is not in correct gripping position. I may grip it on the edges in a different angle, or even if I only see parts of the part, I can still access it. And since I then don't know if the part is placed correctly in the gripper, or I'm even sure it is not, I won't take the part out of the container. I will just drag it more to the middle, place it there, move the robot out, and we will start over the process again with a new picture. And then exactly this part that we just separated will be accessible for a defined grip and then taken out. So let's talk about our next topic, customizable robotics. We will discuss a lot about flexibility and collision freeness now. So first of all, collision-free gripping. To ensure that the robot won't collide during the operation with the container or anything else in the robot cell, we do check the robot geometry with any interference geometry that is visible for the camera, the containers, different workpieces, and also the CAD layout of the robot cell or different restricted areas by the robot program itself. This happens in the software side when we plan our path for the robot, and after that we come to the collision avoidance and collision monitoring in the physical world. Because, for example, you decide that you can and you would like to use a magnetic gripper to take out the parts, then you do need to get the gripper in contact with each parts, and you need to push it a little bit. So to avoid collision, you can use spring-mounted gripper units. And in addition to that, we always use the monitoring of the axis torques of the robot to stop the robot in case we need. So how does this work, and how do I get a high level of autonomy by doing so? So let's have a look at this little graph here. So on the horizontal axis, you can see the cyclic reading that happens every few milliseconds. And on the vertical axis, you can see the X torques here only for one axis visible for a robot system, it will be 6 axes, but it won't be good to read. So here we have visible 2 stops, the soft stop and the hard stop for collision prevention. Let's have a look at the green axis torque movement. We have a robot movement, and when going into the box, it goes above the soft stop level between 2 cyclic readings. Then the system will stop the robot in its movement, and we will fully automatic move the robot out of the box and start over again with a new picture and a new planned path. But for example, if there happens any accident that the robot gets between 2 cyclic readings above the hard stop level, the robot will be set to a complete stop, and then you need to check manually, has there been any damage? And if not, you can reset the robot on the HMI and it will stay in process. So the best part about bin picking is the high flexibility, and especially on the gripping system, because you can adapt to any part geometry and to any material just as you like to do. You can do bin picking with clamping in a parallel way, inside clamping, outside clamping. You can use centric grippers, magnetic, vacuum, or even combinations of them, because if you do use a quick change system, you can say, for taking out the parts with a defined grip, I use a 2 fingers parallel gripper, and for separating, I can use a magnetic gripper to just direct the parts to the middle.
Kevin, let me interrupt you. We have a very good question for the slide before. How time-consuming is it to program and set up the robot system when switching to other raw parts?
There's like absolutely no effort you have to do then, because the system has a lot of front-loading and preparation. So if let's go to the HEV again, a new HEV comes, loads new parts, and then tells the bin picking system, listen here, it's not part type A anymore, it's now part type B you have to manufacture. And if you can use the same gripper system, or if you use a fast changing gripper, you don't have to do anything here. The program will be changed over by the PLC, and you don't have to do anything in case of programming or setup.
Okay, thank you.
So back to gripping systems. Therefore, like I just mentioned, we do not have any setup time, or even if we do, if we have to change over between different parts by hand, we rarely do have to change more than just the gripper system or even the gripper fingers, which can be done by 2 to 4 screws that have to be loosened and tightened again. So the setup time that you need to is very, very low. So let's go on. Last part of today's webinar, we want to show you a cell concept that we developed and brought into the field and is already in production. So let's have a first look at the layout. On the right side, we can see our machine, and then we have the different stations in the bin picking cell. On position 1, we have the bin picking system themselves. We have the camera and the raw part container where we will pick up and separate the parts. Position 2 will be for regripping station to place the parts in a prism for proper orientation and a defined regripping. On 3, we do have the machine shuttles that are very tightly tolerated, so we need those regripping stations. And on position 4, we have the palletizing for the finished parts. Also in this layout, we have an implemented special sequence for blister and SPCs. So we have a docking station for different grippers. On position 5, a blister magazine where the robot will fully automatic change the grippers. On 5, take up blisters on position 6 and lay them on the finished parts. And we do have an SPC drawer for removing parts, manual measuring, and feeding them back into the system. So let's have a look on the cell itself. So here you can see the VL150 dual machine on the right side and the bin picking cell on the left. We have an OP1010. And now you can see that the parts that you remembered earlier are processed in this cell, even though they are not perfectly for bin picking. Still, it's possible. You can see how the parts are placed on the machine shuttle. We have less than 1 millimeter of tolerances here because the parts are clamped between 2 fixed pins and 1 flexible pin to maintain a proper orientation for the pickup system in the machine itself. And here the robot placed the finished parts onto the first layer. Let's have a look for the challenges that we had on this project. First of all, we had complex parts. Surface was shiny, the geometry of the parts was repeating and interlocking, and there we also had a very fast cycle time because every part we had to bring out in 30 seconds. And additional to that, we had some special processes for blister handling and SPC that had to be done during this time too. So let's have a look at a second video that was made after implementation on site. Here we can see the robot diving into the parts, picking out the best accessible. Here we do have the regrip on a different orientation to maintain a proper feed into the machine. Here we have the placing.
During the videos playing, Kevin, another question, is it possible to integrate engraving and measuring in the cell?
Yeah, absolutely, yes. You can integrate any other machine into the process for the robot. May it be graving, may it be measurement, may it be some blow-off or a second machine. You can also take the parts out of the first machine and feed them into a second or onto a conveyor for a larger automation process. Everything of this is syncable and can be done.
So we are happy to react to the customer's demand, right?
Absolutely.
Great, thank you.
So with that said, we are already done with today's webinar. I hope you enjoyed it. I hope you got some new informations that you can use for yourself, or if you do have any further questions, please feel free to ask them. We'd really like to answer.
Indeed, we have another question. Can all parts be picked from the container, or are some raw parts left behind? That's a very good question.
Yeah, it is. With an optimized bin picking system, you can take out all parts of the container, but you have to spend in some effort to do so, because you have to optimize the system regarding to what types do you have, what containers do you have, can you use inlays, what gripper technology do you want to use, and do you have some changeovers in grippers? It is possible, absolutely. You can take out all parts.
Okay. Thank you for your questions. Before I say goodbye to you, I would like to invite you to the AMB, which will take place in September from the 10th to the 14th. As my colleague mentions, we will have also the MRC, the modular robot cell, on the exhibition and other innovations. I hope to see you there and to getting to know you in person. So thank you from my side and see you soon.
Yeah, also thank you from my side. It was a pleasure. I hope you enjoyed the webinar. Thank you for your attendance and have a great day.